Thank you very much, and hello. On behalf of FRILO, I would like to welcome you to the webinar Unlocking the Power of FRILO and SCIA. My name is Florian Ringgut. I work at FRILO in the fields of product management, quality assurance, and customer service. I am very pleased to present to you the advantage of combining SCIA and FRILO, as well as the general approach of our FRILO programs. Our approach is very different from SCIA's working method. In SCIA, all calculations are using a complex 3D model. And let me just say that we are taking a different approach in FRILO. But first, a few words about the general settings during this webinar. The first point of the agenda will be a short introduction of FRILO, who we are and what we do. Then the main part of the webinar will be the basic know-how of the FRILO building model with the connection to the other FRILO design programs. After this, I would like to present to you how the data import from FRILO to SCIA works. And at the end of my presentation, I am going to show you some other interfaces like the brand new FRILO BIM Connector and our connection to Allplan. After all this, I will be happy to answer some of your questions. So, but first, let's start with some quick words about FRILO. Who we are. We are known for our innovative solutions for structural analysis and structural design, and also for the quality and innovative strength of our software services and partnerships. We have over 40 years of experience and a market share of more than 60% in the German-speaking area. We offer over 100 tailor-made software solutions for by now more than 5,800 customers, and they have more than 500,000 of software licenses. In 2019, we generated sales of more than 7 million euro, and with 65 colleagues in the team FRILO, we stand up for you every day. What do we offer? We offer software solutions for all kinds of constructions, like solid constructions, roof timber, foundations, masonry, and all kinds of steel constructions. For the calculation of framework systems and structures, we provide our Stabwerk RSX, and then of course our building model for the calculation of the load transfer of a complete building, and some additional options for the calculation of earthquake and horizontal loads, as well as mass determination. In the future, you can rely on the FRILO BIM Connector to further digitize your office and to meet market requirements. So what defines us? We are developed by experienced civil engineers and tailored to daily tasks of an engineering office. We place great value on our user-friendly and visually appealing interface so that everybody can use the program interactively and easily. And of course, our programs are adapted to the currently applicable standards. And if you have a question or a problem, our qualified service team will help you via email, telephone, or TeamViewer. So in this part of my presentation, I would now like to show you the working method of our building model. And furthermore, I would like to show you the workflow from the building model to the individual component design programs of FRILO. So first of all, I would like to give you a short overview of the possibilities of our building model. For this, I will tell you something about the vertical and horizontal load transfer in general. Then I will show you the building components and loads and how they can be entered and which interfaces are available. And after this, we want to look at how and where the loads and material data of the building components are transferred to the FRILO design programs. But now let's begin with the vertical load transfer. The building model calculates the vertical support forces using a plain finite element calculation on each floor, and both the entered loads and the dead weight of the building components are taken into account. The support forces calculated at the base of the building components are distributed evenly over the length of the walls, and they are all transferred to the floors below. So the program calculates the vertical loads downwards from floor to floor. And this is executed until the program does not find any further building components, like a ceiling, a wall, or something else, and at the base of a wall or a column. So if the program does not find any more load-bearing building components, a foundation is created at the base point. So this allows the foundation loads to be calculated quickly and reliable. The horizontal loads are distributed to the walls and columns which are defined for the horizontal load transfer, and this is according to their bending stiffness. And these horizontal loads can be entered manually or calculated internally by the program for wind, earthquake, and inclination. Each moment at the foot of a stiffening wall, resulting from the height of the floor, is converted into a force couple and applied to the floor below. So if the system does not find a load-bearing wall, the resulting load is distributed to the other walls in this floor via a finite element calculation. So this means that even non-continuous stiffening building components can be taken into account. The entire calculation in the building model is always performed for the characteristic loads and is therefore completely independent of the safety concept. But to transfer the building components to the corresponding design programs in FRILO, the design standard can already be assigned to the building components in the building model. And also in the building model, the action groups are already assigned to the load cases, which are also required for the transfer to the design programs. And this enables a simple transfer of the loads and the support loads to each design program. So now let's take a look at the calculation approach. The building model is not based on the approach of a folded structure. Therefore, there's no three-dimensional calculation like SCIA does. Each floor is considered individually, so the calculation takes place floor by floor. And this means that a wall in the basement is unaware of the stiffness of a wall in the upper floor. And only the bearing forces of one floor are transmitted to the floor below. For the horizontal load transfer, only non-displaceable systems can be considered. Something like a pure frame system would become too soft, as the frame effect cannot be taken into account. So now let's take a look at the input of the floors. There are different options for entering the floors. Of course, the building can be entered using coordinates via the graphic interface, and a floor can also be entered using an imported DXF file, and this file is inserted as a background file, and the program can use the data from this file as snap points, and this is for the input of all building components and loads. Then it's also possible to import the building data using the interface to CHD programs such as Alplan or Glaser. And after the calculation, the design results can be transferred back to these CHD systems. I will tell you later more about this. But now let's take a closer look at some of the graphical input and the load input in the building model. As this webinar is intended to give you more of a general overview of the building model, we will now assume that I have already entered a floor slab into my building model. And therefore, I would like to show you some, I would say, special features when entering a building with our FRILO building model. At first, the program always offers an overview of all entered floor levels. And there it is always possible to rename these floors as I wish. So now that I have entered my first floor as a slab, I wanted to define some loads on it. The vertical loads are entered floor by floor and defined according to their action group in different load cases. The loads in one load case are always applied together. So be careful, there's no automatic recognition of the unfavorable load position of a surface load. So a load distribution by fields is only possible with different load cases. So now let's assume that I have now entered all the loads on my first slab. And now I can open an overview of my already entered floor in the program. And there's the possibility to couple a whole floor with all of its components and loads. And let's say, for example, I copy my existing slab one floor up. Then the program asks me if I want to copy the data of this slab into my new floor. We accept by pressing yes. And then the program copies my entered slab upwards and renames it. So now we can create our building very easily and quickly. In this example, I have copied my entire ground floor up 3 times. And just the same way, I copied my ground floor down once to create my basement. And of course, I can still adapt these floors as I want to. And in this example, I adapted and enlarged the basement as an underground car park. So now let's go back to the interface of the building model. And here it is always possible to display the model in a 3-dimensional view. With this button, you can open the 3D view. So here we can see that I have copied my ground floor 3 times up and 1 time down and adapted a larger basement. So now I could also copy the left building to the right side of the basement just with using one single function in the building model. Or I could simply enter a different geometry on the right side of the building. It's also possible to create a floor using an auxiliary foil. In addition to DXF foils, the building model offers the possibility of define an already entered floor slab as a foil. So in my example, I can create a foil from the ground floor that I have already entered, and I can freely choose the color of this foil. So here you can see in gray that I'm working in the basement, and the program shows the auxiliary foil of the ground floor in red. And now I can enter my building components more easily and more precisely. And it also shows me that in this area, I have two columns which put load on the slab. So I can quickly see that some load-bearing building components are still missing there. So let's say I've now entered or copied the different floors of my building. I have entered or copied all the loads. And with this section here, it is still possible to change or edit single building components. So I can still add some columns, walls, or beams, or I can move them or delete the existing ones. And once I've adjusted everything, I can now calculate my building. After the calculation, it makes sense to check my resulting vertical loads. So we can see that the loads of the upper floors are always applied as superstructural loads to the floors below. So I can find this number here, this number here, this number here. So you can see how the load transfer to the basement works. So in my example, this results in a total load of about 50,000 kilonewton. So now I'm finished with special graphical input and load input of the FRILO building model. And this leads us to some information about the building components and how to transfer loads and material data from the building model to some other FRILO programs. So let's say our building is entered completely. We have checked if all the loads are entered correctly. And now the big question is, can I construct the building according to the architect's concept? So, but before we do this, I would like to give you a short overview what can be transferred from the building model to the other FRILO programs, as you can see here. So, of course, you can transfer slabs to the program slabs with finite elements, PLT. You can also export walls, or we can export to some masonry programs like MWX+, which is able to handle the horizontal loads. Then, of course, all three types of columns, steel, timber, concrete. We can perform a punching shear check with the program B6+. Then, of course, we can export some beams to the program Continuous Beams DLT, which is one of the most used programs in FRILO. And of course, all types of foundations can be exported, like reinforced raft foundations, single foundations, or everything else. So now let's see how we can access our design programs from the building model in our example. This is one slab from our building. And as we can see in the lower area of the slab, the area is very wide, approximately 9 meters, and the slab is only 22 centimeters thick. So I have to think about if this is doable and what's about the deflection of the slab in this lower area. And then we should also look at the punching shear check of one of these columns. And of course, we also have to check the columns itself and the foundations. But first, let's say we transfer this slab to our finite program PLT and check this lower area. So for this, we choose design checks in FRILO and plate analysis with finite elements, and we export this slab to the program PLT. So let's say we have transferred it and calculated the slab in the program PLT. And here we can see the deflection in state 2. And we also can see that we have a max deflection of more than 90 millimeters. So the slab cannot be constructed in this way. And yes, it's too large deflection. But before we think about this, we should also check the shear reinforcement. And if we look at the column at the bottom edge, we can see that a punching shear check is necessary, and we can expect large loads at this point because of the large reinforcement needed. So now we have two options. We can adjust the thickness of the slab, or we can add some supports. So let's say we choose to add some columns. We are still in the PLT program, and here we click onto column and choose several. we decide to add 3 more columns in the lower area. And after we have placed our columns, a pop-up window appears. And there we are able to set all the values of the columns that are necessary, like the form, the dimensions, the material, or the bearing conditions. So now we have placed these three columns, and now let's calculate our slab and take a look at the deflection of the slab again. So now the deflection is reduced from over 90 millimeters to less than 14 millimeters. So the slab can remain 22 centimeters thick with only these 3 added columns. So let's say we are finished with our adjustment of this slab, and let's go back to the building model. When we close the PLT program, the building model asks whether I want to transfer the changes to my building. In our case, these 3 new columns. But I have to say that this only works if the building model is opened in the background. So let's say we want these three columns in our model, and we confirm by clicking on yes, and then they are transferred to our building model. But let's check this via the 3-dimensional graphic in the building model. So now we can see that the columns were only transferred for 1 slab. And since I have only exported 1 slab to the PLT program, this makes sense. But we need these columns in each floor of our building. So in the next step, we go back to the building model and we go to the next slab. Let's say we go 1 slab down. So now we can create a foil from the already adjusted slab to see where our columns must be placed. Then we enter once again these 3 columns, and in the pop-up window we now select applies to all floors. And then our 3 new columns are added to all the existing floor levels of our building. And the program notes that these 3 the columns are already exist on the top floor and will not create double columns. So now again back to the 3-dimensional view of our building, and now we can see that our the columns are in the entire building, and a load transfer is ensured. So in the next step, we want to look at the punching shear check of one of the new columns. So we are still in the building model, and in the menu Design Checks in FRILO, we click on the button Punching Shear Check B6 Plus and select one of the new columns. In the pop-up window, we can see that the program already knows which type of column we have selected and shows us the shear force. But before we go on, let's check how the shear force of 86.6 kilonewton is composed. In the building model, we can display the supporting loads for each load case. The permanent load from self-rate is about 68.4 kilonewton, and the payload from load case 1 is 18.2 kilonewton. And this gives us a characteristic load of 86.6 kilonewton, which is exactly the load the building model transfers to our punching shear check program. So now let's go on with our punching shear check in the FRILO program B6 Plus. Here we can see that the program automatically imported the geometry, the shear force, and all the boundary conditions. In the lower right corner, you can see that the utilization is only at 86%, and so no additional reinforcement is necessary. So that means that the slab can therefore handle this column load with no extra reinforcement. So okay, but we have added more than just this column. What about one of our new inner columns? So let's analyze the punching shear of one of these inner columns, like before, via the design checks in FRILO. We click on the button punching shear check B6 plus and select one of the inner columns. The selected column has a much higher shear force of nearly 280 kilonewton. So after we have confirmed with OK, the FRILO program B6 plus opens like before. And in the lower corner, there's now something in yellow. And if we click on the button checks in the upper menu bar, an advice window pops up. And this tells us that some punching shear reinforcement is required. So let's add some reinforcement, but how and where? In every plus program from FRILO, you can use the search function if you don't know where you can find any import. If we search for the punching shear reinforcement, it's enough if we type the beginning of the word reinf. The program then offers you a selection of possible inputs. So now we know where to enter our reinforcement. And after we have added some reinforcement of our slab, the utilization turns green. And if we click on the check button, we can see that now no more extra punching shear reinforcement is required. So okay, after the punching shear check, we now want to look at some of our edited columns itself. So we go back to the building model, and via the design check in FRILO, we click on the button reinforced column B5 plus and we select one of the new columns. In the pop-up window, we can see that the column goes from the basement to the third floor, and the program already knows which column we have selected and in which floor level we are. You can see the little dot. So now I can choose if I want to calculate a system with all these columns working together from the basement to the third floor as a chain of pendulum columns, or if I just want a system with one column in my selected floor. But let's say I want all columns together, and we confirm this pop-up window by pressing the OK button. Then the program B5 Plus opens, and here we can see all columns from each floor as a chain of pendulum columns, and they are all fixed to each slab of each floor of our building. The program calculates all the required reinforcement per section or per segment. And as we can see, the reinforcement is displayed in green, so it's okay. But down below, there is some warning in yellow that says that the creeping is exceeded by 3%. Now the question, where can I find some information in the program about creeping? This time, I don't need to use the search function because some very important settings are shown on the main graphic interface of the Plus programs. If I click on the text that has something about creep factor on the interface, some pop-up window opens, and there I can switch to ignore creep effects, and the program will not calculate with creep factors. Here I just wanted to show you how simple it is to change some relevant parameters for the calculation via the graphic interface of our programs. So after we have ignored the creeping, the yellow node disappears, and now we can look at the reinforcement of our column. In the program, we can click on the button Edit, and to open a dialog to adjust the reinforcement. In this dialog, we can choose one of our 5 segments of our column. And let's say now I'm in segment 2. And here we can adjust all the necessary reinforcement of this column. When we are ready with this, we can save this position to our static and we can go on. But before we do this, let's check if the loads applied here can be verified within the building model. So in the program B5 Plus, we go to the internal forces and look at the axial force. The design force is calculated with 1,505 kilonewton at the bottom of the column. So now we look at the output of the building model and go to our column. And there we can see each load from each floor separated in permanent loads and payloads. So now we can convert these characteristic loads into design loads. And this gives us a total design load from the building model of 1,503 kilonewton. So the loads calculated in the building model are therefore correctly transferred to our reinforced column in the program B5 Plus. So after we have finished the column, let's take a look at the foundation of our building. So we are back in the building model. If we don't enter a base slab in the program, the foundations are automatically created at the base points of the last load-bearing building components. So in order for the program to be able to dimension the foundations, we have to specify certain parameters in the building model. So for this, we have to click on the defaults of foundation button and enter a value for the characteristic soil pressure. And with this characteristic value, the program calculates the dimension of the foundation based on the characteristic foot loads at the bottom of each load-bearing component. So what we see here is only a pre-dimensioning made by the building model. So now we want to calculate one foundation with another FRILO program, let's say the FT Plus. So we click on the left side at the button Foundation FT Plus, and let's say we choose one of the foundation under one of our new columns. So now the FRILO program for isolated foundations FT Plus opens. And as you can see, the building model chooses a measurement 2.22 for this foundation, which are almost fully utilized. So the program converts the characteristic soil pressure to a soil pressure resistant with the factor of 1.4. And the program also calculates the reinforcement, and this can be adapted and exported if necessary. But now let's check where these two loads come from. We have a permanent load of 940 kilonewton and a payload of 212 kilonewton. So let's again go back to the building model and check these loads in the building model. And yes, in the building model, it is possible to look at the sum of all permanent load and the sum of all payload at the bottom of each load-bearing building component, and this is possible in each floor. So if we go to the basement and look at the column above our exported foundation, we can find the same permanent load of 940 kilonewton, and we can find the same payload as we have seen in the FT Plus program. So again, the loads calculated in the building model are correctly transferred to the foundation program. So after we have looked at the foundation, since we are finished with the main part of the presentation. And in the next step, I want to show you some of the interfaces that are already implemented and some of our new interfaces. In the FRILO programs, you always have the possibility to transfer loads to other building components, of course. And like I have already shown, you can transfer loads from the building model to the design programs. But there are also some external interfaces, like the import of 3D data from Allplan. And also you can export the selected reinforcement from FRILO programs to Allplan and Glaser. So it's like you can do it also the other way around. And on top of this, we have implemented some new interfaces. Since 2019, it is possible to transfer 3D data from the building model to SCIA Engineer, which I want to show you in the next slides. But also there's the brand new FRILO BIM Connector, which will be introduced in the next release. And I think the next release will be launched in about 3 or 4 weeks. But now let's take a look at the interface from FRILO to SCIA. So we are back in the FRILO building model, and we have already finished the input of our building. So now there's an option to export my whole model to SCIA. For this, we just have to click via File on Export, and there we have the option to choose the export to SCIA via Excel. So then the program automatically creates an Excel file with all the data that is necessary for the transfer. And after we have selected a location for our Excel file, a transfer window appears in the building model. And this protocol contains all the adjustments that may be necessary and that still need to be made in SCIA. And it is important to know that the SCIA version to which this file applies is listed in the protocol. So after we have created the Excel file from the building model, we can now import this file into SCIA. In SCIA, it's also very simple. You just have to click on File Import, and there you can choose the option FRILO Geo Building Model. So then our model is imported into SCIA, and it's included all the loads and bearings. So now you can continue calculating in SCIA with the building created in FRILO. And this has the advantage, for example, that we in FRILO, we only use the simplified response spectrum method in the building model for the earthquake load case. And if it's necessary to calculate the earthquake check by using a 3D analysis, you can quickly transfer this building from FRILO to SCIA. At the moment, only files can be transferred from FRILO to SCIA. The way back does not exist yet. So now I would like to show you some of the interfaces between FRILO and Allplan. So I have opened the surface of Allplan and would now like to transfer a slab to FRILO. By now, it's only possible to transfer one slab at a time to our finite program PLT. And once I have selected a slab, I can transfer it directly to FRILO using the transfer options in Allplan. So let's say I choose this slab. Then FRILO will open automatically. And in the FRILO FE program, we now can edit all the loads and calculate the slab. And after this is done, we know all the required reinforcement for our slab. So, and now it is possible to return this information back to Allplan. And after I have saved the FRILO position, Allplan asks me where I want to save and implement these results. So for example, I select the upper reinforcement and can now place the results behind my slab. So now the results of the FRILO calculation are also displayed in addition to the slab I've already entered. So I immediately see that the largest reinforcement is needed in the area of these two inner columns. So now in Allplan, I can start to reinforce my slab. So now let's say I have placed some mesh reinforcement all over the slab. And while I'm doing this, Allplan automatically adjusts the color of the reinforcement still required. So all areas that are white don't need any further reinforcement. So I realized quickly that I still need some reinforcement above the inner columns. And I can continue with my reinforcement. This was only a small view of the interface between FRILO and Allplan. There's much more. But now I also want to give you some information about our new FRILO BIM Connector. So with this tool, you can, for example, import an IFC file received from an architect. So, but architects usually work with a structural model, like a volume model. And to transfer the model into any static program, it needs to be converted. And all the relevant components must be related to the building axis, to the component axis. So this is possible in the FRILO BIM connector with just one click. And this option allows you to convert the imported structural model into an analysis model. So now we have an analysis model with which a structural engineer can continue working. The system axes are all connected and all building components are detected, such as beams, columns, walls, slabs, foundations. In the graphic interface, we can see that the whole building is displayed in red. So this means that no material is assigned to the different building components. So in the FRILO BIM connector, it is now possible to choose a material for the whole model or only for an individual building component. And in this case, the whole model was assigned the material reinforced concrete, and therefore it is now shown in gray. I could also change some material to masonry or to wood or something else. But here, everything was assigned to the material reinforced concrete. So once we have converted our building into an analysis model and all the building components have the right material, let's say, we can export a slab to our FRILO program PLT. And in this example, let's say the upper floor slab is to be transferred to our FE program PLT. So all you have to do is to select the slab and to click on this export button. So then the FRILO program PLT opens and the slab can be calculated. So here you can see the exported slab with the calculated FE mesh. And with the upcoming release, as I told you, it is only possible to transfer a single slab to the program PLT. But in the future, it will be possible to transfer not only the building model, but also some building component programs like columns, beams, foundations, or else. So this brings me to the end of my presentation. I hope I was able to give you a general overview how FRILO and the building model work. And I hope I was able to show you the advantage of the load design in one model, but the component calculation in individual programs. So we still have some time left. I'm therefore checking with my colleague, Mr. Frank, to see whether any questions have already been asked in the chat. But I would like to say that all questions that we do not answer live right now, we will, of course, answer afterwards via email.